When we build AI that simply answers questions, we monitor what it says. But when we build AI that acts autonomously, we have to lock down what it does. Agentic architectures collapse natural language into executable commands. Take a look at this console. The agent on the left is asked to summarize a simple web page. Instead of generating a summary, it reads a hidden payload, silently packages the user's secure session tokens, and posts them to an attacker's external form. Traditional web application firewalls miss this entirely. They are built to catch malicious code or SQL injections. This attack manipulates semantic logic using plain English. Today, we are going to fix this. Open your IDE and pull up your basic agent script. We are going to build a defense-in-depth sanitization pipeline. Step by step, we will take a vulnerable web scraping script and lock it down so it can detect, filter, and neutralize semantic attacks before they reach your infrastructure. The first thing we have to understand is where attackers hide their instructions. When an agent scrapes a web page, it reads the entire document object model, or DOM. You won't see these instructions on the page. Attackers use zero-sizing techniques, setting CSS properties like 0-pixel font sizes or 0 line heights. The text is completely invisible to a human user, but fully readable to your agent. They also use off-screen CSS positioning, rendering blocks of text far outside the visible browser coordinates. If your agent analyzes images, attackers will slip natural language commands directly into the CData tags of SVG vector graphics to exploit your multimodal models. And if your agent reads metadata, they will cloak their payloads inside benign HTML attributes, like simple data fields. These commands can live anywhere in the document. If you let an agent ingest unverified web pages, you are letting an attacker drive your system by proxy. The root of this vulnerability is architectural. Untrusted web page data mixes directly into the exact same context window as your trusted system prompts. An injected payload then poses as an authoritative developer instruction, hijacking the path and overriding safety rails. To fix this, we have to create a strict trust boundary in our code. Go to your agent's prompt template. We need to isolate the external content. Take the variable holding your web scraping results and wrap it entirely in explicit XML style tags, like untrusted content. Next, append provenance metadata to that chunk. Tag it with the exact source URL and assign it a low-trust classification so downstream processes know exactly where it came from. Now the data is isolated. We've drawn the boundary. But drawing a boundary is only step one. We still need an active filter to ensure the agent doesn't execute the logic buried inside that tagged content. Even with the data quarantined, if the agent's planning module reads a command to execute a tool, it might still try to run it. We solve this by adding a semantic classifier into the pipeline. Classifiers like LLM Guard or Guardrails AI evaluate the actual meaning of the text. Position this classifier upstream to inspect every chunk of untrusted data before it reaches the planning module. Configure it to look for authority impersonation and instruction-like patterns, scanning for phrases like important to stop them cold. In your script, write a fallback function. When the classifier flags malicious text, it should drop the payload entirely and return a simple sanitization error to the agent instead of the raw web page. This semantic filtering acts as a logic-based firewall. It catches the natural language manipulation that standard binary defenses ignore. Now for the final layer of defense. We need to limit the damage in case an attacker manages to slip a payload past the semantic filter and coerces the model into calling a tool. This is where we address excessive agency. If an agent has more permissions than it needs, an attacker will exploit them. We have to strictly scope our tool parameter schemas. Open your tool definitions. Rewrite them to enforce a hard limit of fewer than 5 parameters per tool. Strip out complex nested objects. Use primitive data types instead, like integers and booleans. The most critical control you can implement here is replacing open-ended string inputs with constrained enums. An enum locks the model onto a predefined track. Because the model can only select from the exact options you provide, it prevents it from hallucinating execution paths or passing arbitrary injected text. By tightly restricting these parameters, you starve the attacker of the flexibility they need to escalate privileges and access your downstream infrastructure.
Time to test the pipeline.
or on your newly secured agent script against that same poisoned web page we started with. This time, the semantic filter intercepts the hidden payload before it reaches the planner, triggering a clean sanitization abort. The agent safely reports that it cannot complete the task due to unsafe content. The instruction data boundary holds. For production environments, your next step should be deploying a sidecar runtime, like Agent Sentry, to monitor all execution traces in real time. AI autonomy is only viable when backed by rigid structural defenses. To protect these systems, we have to move past simple prompt validation and start enforcing strict system containment.